Thanks for tuning in. The title of my talk is What the Spec, and we're going to be talking about the new features in the Apache Iceberg table format V3 specification, which we call a spec. Just to give a quick heads up, this talk was written by Danica and myself, but unfortunately Danica isn't able to be here today, so I'm going to do it in her stead. But just so everyone knows, both of us did work on this, and if you want to know why you should care about who we are and what we have to say, well, Danica is one of the lead developer advocates at Snowflake for open source software, has done lots of open source software in the past, and I am a member of the Apache Iceberg PMC, the Apache Polaris PPMC, and I've also done lots of open source software in the past. So we're two great people to listen to tell you about all the new things that are happening in Apache Iceberg. Now, before we get into the new things, let's talk a little bit about what Apache Iceberg actually is so that we kind of have a baseline of discussion. Now, to start with, it's really a set of rules. Basically, English sentences that are written into a document that we call the specification, which tell you how you interact with an Apache Iceberg table. So for example, when we talk about how to add files, we say new files have entries added to a manifest that contain their metrics stored as serialized binary, so on and so forth. Basically, a lot of English explaining how you actually do something with an Apache Iceberg table. But the Apache Iceberg project also has a reference implementation in code backing all of this up, where we actually have Java code which implements this set of rules. Now, the important thing about the Apache Iceberg project is that it has these rules first. And one of the reasons that we do that, rather than doing code first and then rules second, is we want to make sure that when we write how to behave with an Apache Iceberg table, we do that in a language and platform agnostic fashion, so that anyone, regardless of what engine they're using, can interact with an Apache Iceberg table at the same level as anyone else. Now, that said, there are actually a bunch of different specifications within the Apache Iceberg project. The one we're going to be talking about most today is the format, the table format specification, which describes how the table itself is built, how you add things to the table, how you remove things from the table, and the basic rules for how you go from one state to another. But there are a bunch of other specifications you might be interested in. There's one for views. There's one describing how an Apache Iceberg REST catalog operates. And there's one for puffin files, which is basically a container for binary blobs, which we can talk a little bit about more later. But basically, you can think of these four things on the left as the descriptions of how you work with Apache Iceberg tables. But the Apache project also has a bunch of implementations itself. So we actually have a Java implementation, like I mentioned before. This is basically considered the reference implementation. We also have a Iceberg implementation, a Rust implementation, a C++ implementation. And then not only that, though, we have a bunch of third parties who have come into the Apache Iceberg universe and have made their own implementation. So for example, if you're using Trino, Trino has its own implementation of a lot of parts of the Apache Iceberg project, but remains completely compatible with any other table written by Apache Iceberg because, again, it follows that specification. And you'll find the same thing for a lot of other vendors. For example, Google BigQuery supports Iceberg tables again by following the specification, but not necessarily using the code that's written by the Apache project. So this is all really cool, but again, how does Iceberg as a table format actually work in the first place? It ends up being basically a set of files which describe other files, which describe other files. And let's kind of build up the concept from the basics. You start out with a bunch of data files. Now, in default, we basically have a bunch of Parquet files somewhere on disk. And our goal with Iceberg is we want to be able to know which files we need to read without actually looking inside of that directory or looking at the data files directly. So what we do is we take metadata from each of these data files and we put them in what we call a manifest file. And you can think of this simply as a listing of data files. So each manifest file gives me a set of data files, which are part of the table at this particular point in time. But we might want to change these around or change the contents of what data files are in the table or not. So we actually have a layer on top of this, which we call a manifest list. The manifest list is basically the complete state of the table at one particular point in time. And it refers to several manifest files, which, as I said, then point to several data files, which if you looked at all of that particular subset of data files, you would be looking at the table at this particular point in time. That manifest list is then referred to as part of a snapshot in a file called the metadata file, the metadata.json. So your metadata.json will basically have a bunch of entries for different manifest lists that indicate different points in time for this particular table. Each manifest list will point to some subset of manifest files, which will point to some set of data files. And then at the very top of this whole pyramid, we will have a catalog, which will basically map a table identifier, like a database name and a table name, DBA table1, to a specific metadata.json. Then again, within that JSON file, we have a bunch of snapshots, which point to manifest lists, to manifest files, and data files. So from a very high level, basically what we've done is associated some higher level files with a lot of lower level data files, which makes it very easy for us to start doing atomic transactions. So for example, say we want to add a set of data files to this table, and we want to make sure that we only succeed if those data files can be added to this particular state of the table. So what we would do is we would add a bunch more Parquet files. We would then create a manifest file, which refers to them. Then we would create a new manifest list, which contains all of our old manifest files, as well as an entry for our new manifest file. So we now have a complete state of the table, which is built off of that first snapshot. We then build a metadata.json file, which includes both our new snapshot, snapshot1, as well as our old snapshot, snapshot0, so that if a catalog is pointing to this, you can actually read either point in time. And then we attempt to atomically swap our pointer for this table identifier from the first metadata file to the second one. Once we've done that, we basically have atomically added that subset of data files. So even if, regardless of when those data files actually land in the directory, they don't become visible to a reader until we do that atomic swap up at the top. If you're interested more in how the transactions are actually built, I would urge you to go check out the documentation or other talks given by me or other folks. But we're going to talk about today instead more of the high-level new things that are coming into Iceberg. So like I said before, there are a bunch of different specifications, and the one we're going to talk about today is the table format spec, which has currently entered its third revision. So the first version of the table format spec was basically the initial release of Apache Iceberg. It said, this is how we're going to do partitioning. This is how we will do schema and partition evolution. This is how we are going to build an Iceberg table and how you will interact with it. V2 was then brought around to introduce ways to do better row level operations. And it basically did this by adding in two new types of file into that hierarchy of different metadata files. It added equality deletes and position deletes. Both of these represented a way of modifying an existing data file in the table without removing it. Prior to this, in V1, the only way to modify a data file would be to delete the previous data file and add a new one with the rows that you wanted modified. This ends up being very expensive if you're only making a few small changes to your data files. So these new data files, or these new delete files, equality and position, were added to basically enable a much faster way of deleting things. Now, V3 has a whole bunch of new changes, and that's what we're going to talk about today. So the main topics I'm going to go over, this is not an exhaustive list of all the things that are in V3, but they're probably the things that are most relevant to users of Iceberg and to good things to know about going forward. Now, we have, most importantly, some changes to the underlying implementation of delete files. So like I said before, we had these things in V2 called equality deletes and position deletes. We have changed the layout of position deletes into something called deletion vectors, which have some additional rules which basically make it easier for us to produce these and maintain tables that have them. There are some downsides to the way we were storing position deletes, which I'll talk about when we get to greater detail on this particular feature. But we've basically tried to fix all of those problems and implement something that's a lot more efficient and less maintenance heavy for the future. We also have added a bunch of exciting new types to Iceberg. One is a variant type. This is really important for folks who have been doing streaming work or things with unknown schema before, because it basically enables you to have a variable schema per row as you're doing new things with your data, while still preserving some of the benefits of having an actual columnar data type with enforced schema. We've also added a geometric type. This is something that people have been asking for a long time. It's very common. And now we have a way of actually storing that within Iceberg tables. And finally, the last thing we're going to talk about is row lineage. The second to last thing we're going to talk about is row lineage. This is a new feature which enables you to basically track the changes that have occurred within an Iceberg table without doing any kind of additional work. And finally, default values. This is another long requested feature for Apache Iceberg tables. It ends up being a little bit more complicated because of how Apache Iceberg tables are set up, but we basically have added some new concepts which let you put in default values for your tables, both at write time and for columns that have not previously existed in your table. So without further ado, let's go into deletion vectors and talk about why they're important and what changes, the changes in them that will have effects on you and your use cases with Apache Iceberg. So let's start out by talking about, again, what are these deletes that we're talking about? So a delete within Apache Iceberg is basically a way of saying, I would like to change the data that's in the table to be something else. Like I said before, in the V1 of the Apache Iceberg table, the only way to do this would be to take a data file, and then if you wanted to remove a particular record, like in this particular example, if I wanted to remove record C, I would take this data file in blue, delete it, and add a new version of that data file, which only has A and B. I can do this atomically based on the procedure I talked about a little bit at the beginning of the talk, and at the end of the day, I have a new table state, which is missing C. The cost of this is that I have to rewrite every single row that has not been modified, which is why this procedure is called copy on write. So basically, when we write the new data, we must copy all of the existing data and ignore the data that's being modified. So there's a very large burden on the writer to copy a lot of data and read things that it isn't actually changing. V2 of the Apache Iceberg spec added two different ways to accomplish deletes, which don't require deleting that old data file. The first is something called an equality delete. An equality delete basically says, instead of replacing that data file, we're going to add a sister file. This sister file is going to basically just have a list of values which no longer exist. So in this case, if I want to delete C from the file at T sub 0, I add a new file at T sub 1, which just has the value C written down. Then on read, this is the merge on read part, on read, I read both of these files. I read the data file that has A, B, and C, and then I read an equality delete file which says don't pay attention to any records that have C in them. Together, I merge this information in memory and can return rows A and B. So you'll notice this is way more efficient in terms of actually marking something for delete than our previous version, because all I have to do is write down the rows I'm removing in a new file. I don't have to copy any of the rows that have not been changed. Now there's a second version of this, because this ends up being a little expensive, because I do have to actually compare all of my values with the values inside of the equality delete files to see whether or not they're removed. We have a different version called position deletes. So position deletes work very similarly, where if I have a file ABC and I want to delete row C, instead I write a position delete file, which tells me which file I'm modifying. So in this case, I'm calling that first file file A. And then we also mark the ordinal of the row which we are removing. So in this case, row A is 0, row B is 1, and row C is 2. So I've written in a position delete file that says, when reading file A, ignore row 2. And in that case, when I merge these on read, I see, okay, I read row 0, which is A, I read row B, which is 1, and then when I get to row C, I see that's actually been marked as no longer existing, so I just don't return it. So this is much faster to actually apply because I don't actually have to compare values. I just look at the row ordinal position of the file, and I just ignore them if they've been deleted. So this is really cool, and we have these actually even more complicated than this. So position delete files had two ways of actually organizing them on write, which had various pros and cons, and are kind of the reason that we decided to go to delete vectors instead. So basically, you would have a set of data files in a partition, and we gave you two different modes of writing these position delete files. First, you could write a partition granularity delete file, which basically said you could write all of these different file names. So for example, I'm deleting from file A, file B, file C, and file D, all in this one particular delete file. or you were allowed to write a one-to-one file granularity delete file. In this case, you would write one file for A, one file for B, one file for D, one for C. Now, in both of these cases, in V2 of the spec, we allowed you to have as many delete files for a particular data file as you wanted. Now, this meant that there was a maintenance burden, because every time you additionally modify one of these data files, you have to make new delete files. And those delete files are going to end up building up in number and causing some small file issues. So regardless of which way you went, you either wrote a bunch of small files just from the get-go that didn't have a lot of information, or you wrote a large file right at the start, but almost all the information in that large file wasn't relevant to your particular query if you weren't looking at every single file in the partition. So we were looking for alternatives, and what we came up with is deletion vectors. So deletion vectors are a concept that's used in some other table formats, and we decided we were going to take some of the best aspects of that and try to fit them into how Apache Iceberg does things. Now, the deletion vectors are basically a complete replacement for position delete files, regardless of what granularity you're writing. The really cool thing about the deletion vectors is we don't actually have any requirements for compaction here. We've set up rules so that when you write a deletion vector, it's essentially one per data file per snapshot, which means you can never accumulate multiple deletion vectors for the same data file. And because their representation is basically identical to the position delete files, the performance is basically the exact same, if not maybe a little better in some ways for scanning performance. So basically better in basically all aspects. Now we're going to store these blobs in something we call puffin files. I mentioned this before, but it's essentially a collection of blobs. This is all very exciting, and you might be asking, how do I actually work with these now? Well, the thing is, when you write these, you will basically be writing a puffin file, which will have a collection of blobs, one mapped to each data file, which has a delete vector applied to it. Then, whenever we want to modify these delete vectors, we simply write a new puffin file and update our pointer so that our pointer no longer points to the vector in this particular puffin file. So now, before you would basically have a file to file map, now you have a file to offset within puffin file map. As an end user, if you're taking advantage of any of the major implementations of Apache Iceberg, you will have no changes to your application code and will basically instantly be using deletion vectors once you've upgraded to V3. The rules we've written into the Apache Iceberg V3 spec say that whenever you read position deletes in V3, you must then write deletion vectors. So basically, if you had position deletes previously, they will instantly be compacted and converted into a delete vector upon your first read and write of those in V3. So maintenance on position delete files is basically completely eliminated. You no longer have to do that. Very exciting. And when you're planning, since we know there's only ever at most one match for a data file, we can do planning a lot faster as well. We don't actually have to aggregate multiple position delete files together to determine whether or not a row has been deleted. So this is all really exciting and happens all behind the scenes. But we also have a bunch of changes that are user-facing. So the first I'm going to talk about is variant type. So variant type is a whole new data type that's been added to Apache Iceberg. You can basically think about variant as that semi-structured data type that you need if your schema is basically untrustworthy. You don't know what's coming in. It might change all the time. If you're ever using a map type in your data, this is basically a better implementation of using a map if you have some kind of regularity to your schema. And at its core, it's basically being stored as two different columns inside of your data files. One which contains the metadata for that particular row, and the other which contains the values for that particular set of metadata. So for example, you might have a row with a single variant, and this variant might have an X, a Y value, and an error value. We would store that schema within the binary portion of the variant, and then in the value portion of the variant, we have a serialized version of the values for that particular schema. So combining these two together, we have a set of rules which are in the Apache Parquet project now, which basically say, if you're looking at an int and the schema portion, this is how you deserialize that value out of the value portion of the variant type. Now, when you look at this, you might say this is actually not very efficient because all I've basically done is built a JSON representation. I built some really complicated representation of my data that still requires deserialization to actually get any real value out of it. And not only that, I basically have lost all the pros and cons, all the benefits of having my data in Parquet in the first place. My min-max values of my metadata and my value columns here are basically completely convoluted from whatever the original values are, so I can't use those for pruning. So the other thing that's been added with Variant is something that's called shredding. It's also known as subcolumnarization in some other papers. So if you've read either of those terms before, it's the same thing here. And basically the idea is that in most of the times we're using some kind of variant data type, there's a few columns that appear all of the time. So you can imagine you might be getting data from a sensor, which always reports X and Y, and then has a bunch of other things which change on version updates. You can imagine some versions add some humidity, some versions have an error that comes up in a different string type, all sorts of other things that can change. And basically within the shredded variant type, we store that metadata and value column as before, but we also allow for typed versions of some of the fields that we know that happen very frequently within that data file. So in this case, we might say that we always see X and Y, and X is almost always an integer and Y is almost always a Boolean. In this case, we see that Y was actually a long for this particular row, so we've put null into its typed version. But for X, we actually have a proper typed integer column in Parquet, which means that if I was using Parquet and I'm doing a scan on X, I can actually use the min-max values for X, even though this column is a variant. It's not actually a fully structured column. So basically on a per file basis, we can set up columns that are extracted out and treated as normal Parquet columnar data with the min-max values and all of the planning and benefits that come with that. So basically you get the benefits of using a variable semi-structured type, as well as the benefits that come with the pruning and min-max value exclusions that you get with a normal real schema table. So this is really exciting. One of the problems, though, is unfortunately, if you would like to use this, you have to add it to your own code first. You have to add it to your tables, and you have to change your user code to actually insert into these variant types. There is support for this in Spark 4.0, and I think a lot of the other engines are working on support as well. There's a reference implementation for this as well within the Java implementation of Iceberg. The other big caveat is that shredding that I described is currently not implemented anywhere yet. I know a bunch of vendors are working on their own versions on how this should be implemented, and I'm sure we're going to end up with a reference implementation as well. But basically, as of right now, you can use variant types, and hopefully in the near future, you'll be able to take advantage of shredding as well at like a production scale. But there's a lot of different folks working on that right now. The next cool type that's being added to the Apache Iceberg table format in V3 is geometric types. This is another commonly requested types, but if you haven't used it before, the reason that we want it is that there are many, many systems already that support geometric data, and we want to be able to store them in Iceberg just as well as everything else. Now, when you store something inside of Iceberg, the important things that we need to define are how you actually do predicate pushdown for this particular type of data, how it's stored, and how partitioning works with this particular data type. We actually don't need to know the ins and outs of exactly what kind of kernel is backing this particular data type or something like that. We just need to know how to express that back to an engine. So in order to make this relatively simple with inside of Iceberg, we basically implemented two different geometric types, one geometry, the other geography. So the big difference between the two of them is one is flat and the other is spherical or spherical-like. I learned more about geography than I cared to when we started implementing all of this, but basically there's a lot of different spherical models for how to treat the globe, and it's very important that you have the right one. So that's stored within the specification, but we aren't having a specific type for all of those different models. Basically, you at a high level are deciding, am I 2D or am I 3D? Now, The reason that we need that is that within Iceberg, we need to be able to say, how will we bound all the values within a particular file? And for that, we're building bounding boxes around them. In the case of 2D geometries, you can basically build a square, but in terms of geographies, you have this fun little meridian problem where you can actually wrap around the meridian. At the low level, we've basically got an implementation again in Apache Parquet, which is then being taken for Apache Iceberg. And basically, if you have a well-known binary representation, that's how it's going to be stored. As an end user, again, if you want to take advantage of geometric types, you do need to add new columns to your table. You have to add new code that actually uses this. But once you've done all of that, your engine should be able to take advantage of the pruning and predicate pushdown automatically. So there shouldn't be any extra work once you've got your data in. Once you have it in, any predicates you push down to this geometric type will automatically prune the correct files. So very exciting there. The next thing I'm going to talk about is row lineage. Just going quickly through this, this is a feature for people who really want to be able to track what's happening to their rows on a row by row basis. Prior to this, once you inserted a row into Iceberg, unless you manually added your own tracking information, there would be no way to tell whether or not that row came from a previous row or was a completely new row to the table. So to enable this in Apache Iceberg, we basically added in two new metadata columns. One is a row ID, which is a unique ID for every single row, and last updated sequence number, which tells you which snapshot that row was set in. So this is all really cool. And the really exciting thing about this is we're doing this at almost no cost to the end user, because unless you're changing rows, we get these values by inheritance through that metadata layer. So the data files themselves don't actually get changed unless we need to update one of these values. So as an end user, this is basically automatically on the moment you have a V3 table, and all writers to V3 tables are required to actually update and keep these values accurate once those rows have been modified. Once they've been written, they're very easy to read by all engines. And again, the semantics for how we write these are a little bit different from an engine perspective, but shouldn't be different for any of the end users. Now, the last thing I wanted to touch on as we're running low on time is default values. This is another really important thing. And basically, previously in Apache Iceberg, you could have optional columns, but if you have an optional column, you basically have to choose null or a value. But we don't often want to do that. Sometimes we want to add a column and say every single use of this column in the past should have a specific value. You can now do that in Iceberg. Now, a similar problem, but actually completely different semantically, is when I specify new rows to my table, I might have certain columns that I don't want to specify. I would like an automatic value to be placed there instead. So we've actually added two different things which are called default values that solve both of these problems. So there is an initial default, which is basically when I'm adding a new column and I want to say any place that this column was not set in the past, please use this value. And a write default, which says whenever I'm writing new rows to my table, use this value if the writer has not explicitly specified what value to use. Now, there's some more cool detail on how this actually works, but we don't have a lot of time. I'll just let you know that if you're an end user and you want to use these, all you have to do is change your table schema. The exciting thing about this is you can use it within structs and all this kind of stuff, but you can't actually use it with more complex types like maps, because the way we actually store these defaults is by serializing their values into the schema, and we're trying to avoid making things overly complex there. So those are some of the cool things happening in V3, but I would be a bad open source contributor if I didn't tell you that we're already thinking about V4. And the best thing about an open source project is that everyone who's watching this video and anyone who would like to at all can join in those discussions. So those discussions are happening right now as we talk about the future of the Apache Iceberg project. So if you have any interest at all, please join Apache Iceberg. We are an open governance project with open code, and we would like everyone to join. We have a Slack, we have GitHub, we have Jira, all that kind of stuff. And of course, if you want to come join me at Snowflake, please let me know. We are doing all kinds of fun open source stuff, and I'd love to hear from you. And that's it. So thanks so much for listening to my talk. I hope you learned some cool things about Apache Iceberg Format V3.